Okay, so now we're recording. All right, so as I said before, get rid of this, all of this here. Um, so as I said before, are there any questions you have to ask about any of those topics? Oh, I forgot. I was about to discuss where to find the tables for somebody asked about the tables for solubility product, right? So if you go to the Canvas shell and go to files and then go to tables. And okay, so the tables with the solubility products would be located right here. And if I download it, you'll see it's about 6 pages long. So that's a table right there. All right. So this is what you'll have access to during your test and the final exam too. And also, I think you have been introduced to this particular table, dissociation constants, which give you the dissociation constants for weak acids and weak bases. All right, so those are the tables that you'll have access to, in addition to the other one, the periodic table and all that good stuff. All right, so I don't remember who asked that question, but I hope I have answered your question in regards to um, what you'll have access to during your tests. Excuse me, give me 1 minute. Let me turn on this fan. Okay. Okay, I'm back. Sorry about that. So any other questions?
Professor,
Yes, sir.
um, I was wondering it was assignment number 6
Okay, let me
on,
let me see if I can bring this up on my other computer here so that
all right.
um close this here. Oh, one more. Okay, so you said assignment 6.
Yes, sir.
Assignment number 6. And what question?
It's question number 5, 5C.
I just lost it. Let me try again. Hold on 1 minute. Assignment number 6. Where is it? Okay. Okay. Assignment number 6, question number 5C.
Yes, sir.
5. Okay. All right. So 5C. Okay. So, well, at the top of that question, it says use the values of delta S and delta HF standard to calculate delta G for each of the following reactions. So for 5C, let me open up will this work? Let me see if this would work. Let me see if this works. Okay, so the equation is NH3 gas plus HCl gas to give NH4Cl, which actually would be a solid, even though it's not indicated there. So the question is asking for you to calculate delta G based on the delta H and delta S values. So if you remember, the equation for delta G is delta H standard minus T delta S standard, right? So what we have to do is calculate delta H using the data from the tables and delta S using the data from the tables as well. So when I look this up, I got that let me start off with the delta H first. So for delta H standard, I found that the value of delta H for the ammonia is 192.43 joules per mole. Um, Hold on 1 minute. 1 minute. I'm sorry, wrong. That was delta S. You know what? Let me do delta S first since I have it here already. So, um, uh, okay, so let me just cross this out and put delta S standard, right? So when I looked up the delta S values for ammonia, that was 192.43, and for HCl, that was
Um,
one. I'm sorry?
Professor,
Yeah.
in class, I think you told us it was 192.45.
Okay, let's go with that. Probably that's correct. Maybe, I don't know. Okay, and then the value for HCl is 186.91. I hope I said that too. Now the units here would be joules per mole Kelvin. So let me include that here, and let me include that here. And then now for ammonia, I'm sorry, for ammonium chloride, it's going to be 94.6 joules per mole Kelvin, right? So delta S standard, based on that, would be equal to the enthalpy of the product, which is 94.6 joules per mole Kelvin, minus the sum of 192.45 joules per mole Kelvin plus 186.91 joules per mole Kelvin. All right. So we add those two. Where's my calculator? We're going to work out what's within the parentheses first. So 192.45 plus 186.91. So that part gives 379.36. Whoops. 36. And you're going to subtract that from 94.6 joules per mole Kelvin, right? So according to my calculation, and again, please correct me if I'm wrong. Let's see here, 94.6 minus 379.36. And according to my calculation, this works out to be equal to minus 284 point, round off to one decimal place, so that would be 8. And this would be joules per mole Kelvin. Joules per mole Kelvin, right? So that's delta S, all right, for the reaction. Now we need to do something similar, but this time for delta H. Um, okay, how can I erase this? Let's see. Okay. So let me erase this line here. Okay, this is not doing a very good job. Let me see how this works out. Oh no, that won't work at all. Okay, so in the case of delta H, it's the same idea, products minus reactant. So for the ammonia, according to what I have here in front of me, I got the value for ammonia as being equal to minus, what's going on? Uh, Oops. Okay, so for ammonia, the value I got is minus 46.11 kilojoules per mole. For HCl, the value I got is minus 92.31 kilojoules per mole. And then for the ammonium chloride, I got minus 314.43 kilojoules per mole, right? So when I'm calculating delta H, it's pretty much in the same way that I would have calculated delta S. So let me erase all this down here. So delta H standard would be equal to the sum of the enthalpy of the products. Well, there's only one product, so that's minus 314.43 kilojoules per mole. And that, I'll subtract from that the sum of minus 46.11 kilojoules per mole plus minus 92.31 kilojoules per mole. So when I get down here, again, I'm going to work out what's within the parentheses first. So I'm going to have minus 46.11 plus minus 92.31. And that part I got to be equal to minus 138.42 kilojoules per mole minus here. And here I'm still going to have minus 314.43 kilojoules per mole. So, okay, what happened? Okay. Okay, I don't know. Okay, so let's do this part now. So minus 314.43 minus, and then minus 138.42 minus, and the answer I got is minus 176.01. So let me write that down here. Minus 176.01, and this would be kilojoules per mole. Now, remember now, the question is asking for us to calculate delta G. So we have determined delta H, and we have determined delta S, and the temperature is going to be 298 Kelvin because the temperature is 25 degrees Celsius, which is standard, which is a standard temperature. So therefore, to find delta G now, we just put the numbers in to that equation. Delta G standard, that is equal to minus 176.01 kilojoules per mole minus T, which is, as I said before, 298 Kelvin, multiplied by delta S, which we calculated earlier. I erased it, but I think I have it here somewhere. Delta S is equal to, okay, I know I wrote it down here somewhere. Oh, okay, so delta S is equal to minus 284.8, and this is in joules per mole Kelvin. But what we have to do at this stage is convert the joules to kilojoules. So we have to multiply by a conversion factor, which is, of course, converting from joules to kilojoules. So that would be 1,000 joules down here and 1 kilojoules upstairs. And that is basically how the setup is. So I'm going to work out this part first. 284.8 divided by 1,000 and then I put a minus sign in front of that, and then I multiply that by 298. So according to my calculation, this part here works out to be equal to minus 84.8 kilojoules per mole. And I'm going to basically do the rest. So according to my calculations, let's see here. So it's going to be 176.01 minus 84.8. And according to my calculations, this would have to be rounded off to one significant figure. I'm sorry, one decimal place. So according to my calculation, this would be 91.2 kilojoules per mole. All right. And that's basically it. Let me do this part again. I think I may have made a mistake earlier. 298
So, Professor,
times, hold on 1 minute. 284.8 and then divide by 1000. Oh, this should be 84 point. Hold on. 1 minute. 298 times 284.8 divided by 1000. Oh, okay. When I read this should be 284.9, right? So let me do the rest now. Plus 176.01 minus, hold on. This should be plus. So 176.01 minus plus 84.9. So this actually should be 91.1 kilojoules per mole. Okay, yes, you had a question?
so when you multiply the 284.8
Mm-hmm.
after it's divided by 1,000,
Mm-hmm.
once you multiply it to 298 Kelvin, it doesn't turn into three significant figures?
Yeah, 3 6 figures, right. That's what we have here. 84.9.
Oh, okay, yeah, okay, that makes
Okay.
sense.
And then you do the rest, all right? Okay, any other
Okay.
questions about this one? Any other questions? Or any other questions about any other topic or other things you need explaining?
Can we go over number 6 on assignment 6?
Okay, let me see if I can find it here. Number 6. Okay, number 6 has to do with that reaction. Okay, let me clear this here. Okay, so in the case of number 6, they gave you this equation, C solid in the form of graphite plus 2H2 gas to give plus half O2 gas, and that will give you CH3OH liquid. And the question is asking for you to calculate Kc for this reaction, all right? So, and they gave you delta GF standard for methyl alcohol is equal, for this, the delta GF is equal to minus 166.27 kilojoules per mole. All right. Now, there is an equation which relates delta GF and Kc, and that is delta GF standard is equal to minus RT ln Kc. All right. But what the question is asking for is Kc. So we have to rearrange this to get Kc is equal to E to the minus delta G standard over RT. All right. Now, how do we get delta G standard for this equation? Well, they gave us delta G formation for this. And it turns out that this equation is basically the equation for the reaction of that produces this, 1 mole of this, right? And remember, we said that if you look at if you look at the tables and you look for delta H for elements by themselves, right? Then they would be zero. So that is true for carbon, that is true for hydrogen, and that is true for oxygen. These all have a zero value for the delta GF, right? Delta GF of the methanol, however, is this value right here. So therefore, we can basically say that delta GF for the delta GF is equal to delta G for the reaction, which is equal to minus 166.27 kilojoules per mole. And therefore, all we have to do is substitute this value where delta G is right here. So that results in Kc is equal to minus 166.27 kilojoules per mole divided by R, which is 8.31 joules per mole Kelvin, times the temperature, which is 298 Kelvin. So all we have to do, and this is, of course, E raised to all that, right? So basically what we have to do now is work out the exponent part of this equation. So let me do that now. 166.27 divided by 8.31 divided by 298. And let me see. And oh, that will be positive. So this basically becomes, hold on, let me see if I did this. Oh, one more thing. How could I forget? I just realized that I should convert the kilojoules to joules or joules to kilojoules. It doesn't matter which one. Because the unit here is in kilojoules, the unit here is in joules. So we have to do some conversion right here. How do I get rid of this thing? Okay, I don't know how I got that showing up. Anyway, basically I'm going to just put right here, I'm going to squeeze in right here the conversion factor for converting from joules to kilojoules, right? Okay, so we need to include that in the calculation. So let me do this again. 166.27 multiplied by 1,000, and then divide that by 8.31, and then divide that by 298. Okay, let me do this again. 166.27 divided by 8.31 times 298. Okay, so according to my calculation, this works out to be equal to, oh, no. Hold on. 166.27 times 1,000. Okay, so according to my calculation, this works out to be equal to e to the 67. All right, in fact, to be more specific, 67.1. So let me do this now, 67.1. Okay, so this becomes equal to, since this is one decimal place, then this has to be expressed to one significant figure, so that would be 1 times 10 to the 29. And that's the Kc value. All right? Okay, any questions about this?
Professor,
Yes, sir.
I'm having a hard time differentiating between delta G and then delta GF.
Oh, okay. So delta GF is the free energy of the formation of a particular compound from its constituent elements under standard conditions. All right. So going back to this example, this is the molecule for which we are given the delta GF value under standard conditions, right? And basically, what that means is that to form this compound, right? Or more specifically, to form 1 mole of this compound from its constituent elements, the carbon, hydrogen, and the oxygen, right? Whatever the free energy change of that is, then that is delta GF standard, right? Of course, standard conditions must apply. In other words, the temperature must be equal to 25 degrees Celsius. If they're in the gases, the pressure will be 1 atmosphere. If they're in the solutions, the concentration should be 1 molar. And so those are the conditions. All right. So that's delta GF standard. Now, delta G is basically the free energy change of pretty much any reaction. You see what I'm saying? And again, if it's delta G standard, then again, standard conditions would apply. All right. So basically, the delta GF standards values that are given in the tables is what you can use to calculate delta GF for a particular reaction. It's basically the same thing as you do for standard enthalpy reactions. It's products minus reactants. Of course, you have to take into account coefficients and all that good stuff. So that's basically the difference between those two. There's only one difference really, and that is that delta GF standard is for the formation of a molecule or 1 mole of a substance from its constituent elements, whereas delta G standard is just simply applicable to any reaction, any equation.
Okay.
Yeah.
Okay.
Okay, any other questions?
Also,
Mhm.
I saw in the lecture you wrote delta G RXN. Is that something different too?
No, that's basically that's saying delta G of the reaction.
Okay, so that's
You-
also
you-
just delta G.
Yeah, exactly. You know, there are
Okay.
some textbooks that, use delta G reaction. It's the same thing.
Okay.
Mhm.
Thank you.
All right. Okay, any other questions? Any other questions?
Can we go over question 3 on assignment 5?
Okay, question 3 on assignment 5. Let's see. Question 3 on assignment 5. Okay, so in this case, okay, so just to make sure we're on the same question, calculate the standard entropy change for the formation of gaseous propane, right? That's a question, right? Oh, no, that's assignment 6. My bad. Assignment 5, you said.
Yes.
Okay, my bad. Assignment 5. Okay. And you said question number 3. Okay, so titration. Okay, so basically, the question is asking, well, firstly, the question gave you the initial amount of sodium hydroxide, right? 12 mils of a 0.0050 molar solution of sodium hydroxide. And I take it you want me to start with the A part, right?
Yes.
Okay, so basically the A part says you're given 6, okay, why is this thing not moving? Oh, okay. You're given 6 mils of a 0.200 m solution. So let's see here. Hold on. Okay, no, I want to know, how do I get rid of this thing? Oh, okay. All right, so the first thing you need to do in order to answer this question is find out the number of moles of each substance, the acid and the base, right? So what we do is find the number of moles of the base, which is sodium hydroxide. And of course, we know to do that, we take the volume, which is 12.00 mils. We convert it to liters, right? And then we multiply by the molarity in moles per liter, which is 0.0500 moles over 1 liter. And when that is worked out, that works out to be equal to 6.00 times 10 to the minus 4 moles. All right. So that's for the sodium hydroxide. And we do something similar for the acid, which is benzoic acid. I'm going to use HA to represent benzoic acid because the formula is not really that important to solve this problem. So the volume in the case of benzoic acid is 6.00 mils. Again, we convert it just like above to liters. 1 liter above, 1,000 mils below, and then we multiply by the molarity, which is 0.200 moles over 1 liter. And when we do that calculation, I got 1.20 times 10 to the minus 3 moles. The next step is that we write down the equation for the reaction between the sodium hydroxide and the acid, and we have to construct an ice table. So the ice table in the initial line will have the amounts of the acid and base initially. So the base was 6.00 times 10 to the minus 4 moles. The acid is 1.20 times 10 to the minus 3 moles. And then you have 0. Of course, you don't need to concern yourself with the water. Now, obviously, this is a 1-to-1 mole ratio in terms of the equation, but we don't have a 1-to-1 mole ratio between the two, which means that one of them would be the limiting reactant. And because it's 1-to-1, we can easily tell that the sodium hydroxide would be the limiting reactant and therefore would be completely used up. So therefore, the change for the sodium hydroxide here is going to be minus 6.00 times 10 to the minus 4. Here we're going to have 6.00 times 10 to the minus 4. And then on this side, you're going to have plus 6.00 times 10 to the minus 4, right? So at the end of the reaction, you're going to have none of this. You're going to have 1.2 times 10 to the minus 3 minus 6 times 10 to the minus 4. And that will give you 6.0 times 10 to the minus 4. Right? And then over here, you're going to have 6.0 times 10 to the minus 00 times 10 to the minus 4. Right? The next step is that you need to find the concentrations of HA, which would be equal to the concentration of A minus, which would be equal to 6.0 times 10 to the minus 4 divided by the volume. What's the volume? The sum of these two, 12 and 16. So that will give you 18.00 milliliters, which you have to convert to liters, 1 liter over 1,000 mils. And then, let's see here, divided by. So this gives, according to my calculation, this gives 0.033336 figs. So we can write it like 3.33 times 10 to the minus 2 m. In any case, the composition at this point is a mixture of a weak acid and the conjugate base of the acid, right? In other words, we are talking about a buffer. And if we're talking about a buffer, to calculate the pH of the buffer, the pH would be equal to pKa plus log the concentration of A minus divided by the concentration of HA, right? But we know that the concentration of HA and A minus is 1. So this will be simplified to pKa, which is minus log of the Ka of the acid. And I think they gave us the Ka of the acid. Let me see if I can find it. Let me see here. The Ka of the acid is 6.28 times 10 to the minus 5. So this will be equal to minus log of 6.28 times 10 to the minus 5. All right? And when I do that, 6.28 times 10 to the minus 5 log, the answer I got is 4.20. In fact, to be more specific, because this is 3 figs, this will be 4.202, according to what I have here in front of me, all right? And that's basically how that is done. All right? Any questions about this? Any questions?
Where do we get the pKa from?
That is given at the top of question, the A part of question number 3. And if you're not given the Ka value, you'll have access to the table, which I mentioned before. So you could look up the Ka value.
Okay.
All right. Okay, any other questions about this? Any other questions?
When you have benzoic acid equal to the conjugate base,
Mm-hmm.
when it's 6.0 times 10 to the minus 4 over the 18 milliliters, how do
Oh,
you
whoa,
know?
hold on, hold on. What are you talking about? Oh, you mean the concentrations here?
Yes, yes, right
Okay,
there.
okay, yeah.
How do you know which 6.0 to use out of the HA and then the NaA?
Uh, to be perfectly honest, it doesn't matter.
Okay.
You could have used the 6.00 here. But ultimately it doesn't matter. You know why? Because they're equal and they will cancel out here and here.
Oh, okay.
You see what I'm saying? So basically
Yep.
pH will end up being equal to the pKa anyway.
And in most of these types of problems, the HA and then the conjugate base will be equal to each other.
No, not in all cases. And in fact, that's the reason why I went through this step, because previously what I would have done is, or what I could have done is that because I would just say that because these two are equal, I would just basically jump right down to here and then to here, right? But the reason why I went through this step is because there are some instances where the concentrations or the number of moles of HA and A minus may not be the same. So what you'd have to do now is calculate the concentration of HA separate from the concentration of A minus, and then plug those values here.
Okay.
You see what I'm saying? So, this is not always going to be true. This is only true in situations where we achieve what is called the equivalence point. All right. Okay. Any other questions about this? Any other questions?
Do you think we could go over a problem then where
Well,
that's not the case? Where
hold on, stick a pin.
okay.
The person who asked me to do number 3, I didn't see who it was. Do you need me to do the others? The B part and the C part?
Can we just go through the C part?
Okay, the C part. So let me find it. Okay, now for the C part, they're asking for the pH. Well, it's a different acid, butanoic acid. They gave you the volume and they gave you the molarity, and they gave you the Ka value, and they're asking for the pH in that case. So let me clear this first. Okay, so now the number of moles of the base is going to be the same as in the one that we just did. We calculated it already. I'm just going to write down the value here. The number of moles of sodium hydroxide. That is equal to 6.00 times 10 to the minus 4 moles, right? So what we need to do now is calculate the number of moles of the other acid, right? Which is the butanoic acid. So to calculate that, we're going to do something similar to what we did before. We take the volume, convert it to liters, and then we multiply by the molarity, which is 0.100 moles per liter. So when I do that calculation, 6 divided by 1,000 times 0.1, so that gives 6.00 times 10 to the minus 4 moles, right? So then the next step is, again, the ice table. So let me write down the equation here. And then the initial row will have 6.00 times 10 to the minus 4 moles, 6.00 times 10 to the minus 4 moles for the sodium salt, for the acid, and then for the sodium salt, this will be 0. Don't need to worry about water. Then the change here is going to be, now in this case, we have equal amounts of both the base and the acid, which means that they will completely consume each other. So therefore, the change here would be 6.00 times 10 to the minus 4 moles. Here is going to be minus 6.00 times 10 to the minus 4 moles. And here is going to be plus 6.00 times 10 to the minus 4 moles, right? So at the end of this reaction, you're going to have 0, 0, and here you're going to have plus 6.00. times 10 to the minus 4 moles. So the question is, what will happen next? Because you have no base, no acid. The only thing that you have here is the salt, which contains a conjugate base of the weak acid, right? So the question now becomes, how does the salt interact with water? Well, there's a two-step process. I'm going to squeeze it in right in this corner right here. The first step is where the salt dissociates to form Na plus and A minus, right? And then the A minus, being a weak base, will act as a base by reacting with water, and this will be an equilibrium situation to form Ha plus OH minus. So basically, we know that the solution is going to be basic because hydroxide ions are being produced, right? So whatever the pH we're going to calculate must be above 7, right? Now, what that means is that we have to construct another ice table. So let me erase all of this here, actually. And write down, what I'm going to do now is rewrite this equation down here, which would be A minus plus H2O to form HA plus OH minus, right? So initially, I'm missing one important step. And that step is, in fact, let me erase this here. That step is that I need to find the concentration of the A minus. So let me erase this here. And let's focus on determining the concentration of A minus that was formed from the dissociation of the sodium salt. That would be equal to the moles of the salt, which, if I remember correctly, we calculated that to be equal to 6.00 times 10 to the minus 4 moles. And then we divide that by the total volume. So the total volume would be, what was the volume before? The total volume would be 18 mils because it was 6 mils from the from here and 12 mils from the initial part of the question. So this is going to be 18.00 mils, right? Again, we have to convert this to liters. So 1 liter over 1,000 mils is what you multiply that by. And let's see what this gives. So this is 6 times 10 to the minus 4 divided by 1/8 times 10 to the minus 3. And according to my calculations, again, this is going to be 0.0333 m. So when we set up the ice table that I just erased, this is what you're going to end up with, HA plus OH minus. So the initial concentration is going to be 0.0333. Here you're going to have 0. Here you're going to have 0. The change here is going to be minus X plus X plus X. Because it's a weak base, we don't know how much of it has reacted. So we're just going to call the change for A minuses to be minus X. And then at equilibrium now, you're going to have 0.0333 minus X for A minus. For HA and OH minus, you're going to have X and X here, right? Now, here I'm going to squeeze in what happens when you write down the KB expression, not KA, KB expression. That will be equal to the concentration of HA times the concentration of OH minus divided by the concentration of A minus, right? Then we put these terms into this equation. You're going to end up with X squared over 0.0333 minus X, and that's KB, all right? Now, we need to assume that X is much smaller than 0.0333, so that KB is now equal to X squared over 0.333. And then we simplify this, or not simplify, but solve for X. That will be equal to the square root of KB times 0.30333. Now, in this case, the conjugate base of butanoic acid, so that's called the butanoate ion, You need the KB for that, but that's not provided in the tables, right? What's provided well, it's not provided in the question either. What's provided in the question is the Ka value for butanoic acid. It's 1.52 times 10 to the minus 5. And if you remember, we said that Ka times Kb is equal to Kw, right? So therefore, we can find Kb by replacing Kb with Kw divided by Ka. So that's what we're going to do here. Hope I have enough space here. Square root of Kw divided by Ka times 0.0333. Okay, let me erase the top part here again. Let me just erase all this here. Okay, so we can put the numbers in to solve for x. That will be equal to the square root of 1.0 times 10 to the minus 14 divided by Ka, which is 1.52 times 10 to the minus 8 multiplied by 0.0333. All right, so let's see what that gives. Divided by 1.52 times 10 to the minus 8. And then I'll multiply. Yes, ma'am.
The Ka value is 1.52 times 10 to the negative 5.
Oh, sorry. Yeah, you're right. Thank you. Minus 5. Okay, so let me redo this again. Thank you for that. 1 times 10 to the minus 14 divided by 1.52 times 10 to the minus 5. And then I'll multiply that by, excuse me, 0.0333. And then I find the square root. And, oh, no, that can't be right. Let me do this again. 1 times 10 to the minus 14 divided by 1.52 times 10 to the minus 5. And then multiply by 0.0333. And then we find the square root. So according to my calculations, this works out to be equal to 4.68 times 10 to the minus 6, right? And based on what we had before, which I partially erased, actually, I should round this off to 2 sig figs. I'm sorry. So this should be 4.7 right here. So this should be 4.7. All right, times 10 to the minus 6. Now, based on the ice table that I had before, X would have been equal to the concentration of hydroxide ions, which is what I had here. So this here would be equal to the concentration of OH minus, right? Now, to find the pH, we need to first find the pOH. So the pOH is equal to minus log of 4.7 times 10 to the minus 6, which would be equal to 4.7 times 10 to the minus 6. And then I find the log of that. So according to my calculation, the log of that is equal to 5.33, which means that the pH is equal to 14.00 minus 5.33. And according to my calculation, this works out to be equal to 8.67. And that would be the answer for the C part. All right. Okay, any questions about this one? Any questions?
So is this a good example then, where you would have to find the concentration of the conjugate base and the acid or base separately?
Yes, but in this case, you don't need to find the concentration of the acid in the first part because all the acid has been used up. You see what I'm saying? I erased the first ice table. If you remember the first ice table,
yeah.
right? All the acid and all the base was used up, right? The only thing that was present at the end of the reaction would be the A minus. So you only have to be concerned with the A minus reacting with water, and that's where we get the second ice table from. All right. Now, if it was like in the previous example, where not all the acid is used up, then you have to take into account the acid, HA, and the A minus. And because that's a combination of a weak acid and its conjugate base, then we can just put those numbers. Well, first, we'd have to find the concentrations of HA and A minus. And then we put those numbers into the Henderson-Hasselbalch equation, and that gives us the pH directly. All right?
Okay. So
Yeah.
then they would be in that equation where it's the products divided by the reactants. That would give you the concentrations for both.
Well, you have to find the concentrations of both by dividing the moles by the total volume, right? So you determine the concentration of A minus by
Okay, so
dividing,
separately.
exactly, separately,
Okay.
right? It's just that in the previous example, it just so happens that they're equal to each other, but that's not going to be true in all the cases. So you have to
Okay,
do
thank you.
you have to do that calculation separate. Which reminds me, somebody, I don't remember if it was you or somebody else, was asking about an example where that would be the case where we have to
Yeah, that
calculate
was
them
me.
separate. That was you? Okay.
Yeah.
I'm not good at creating questions. So what I would have to do is do a search. So let me see if I can find any let me go here. And okay, what should I put here? Weak acid, strong base titration problems. Let's see if I can find a problem where that is so. Try the next page. Let me see what this says. $50 mils of 0.1. Oh, okay, this is just how to plot a tide. Okay, you know what? Let me go back to hold on. I know what. I'll go back to the first problem, but I'm going to change one number. Let me go back to the first problem. Okay, so the first problem, it was 6 mils of 0.2 and 12 mils of 0.5. Let me see. Okay, you know what? Okay, I'm running a bit of a risk here because like I said, I'm not good at creating problems, but I think this will work. So let's say you're titrating, and let's say that the for the sodium hydroxide, right? Let's say that the molarity, the concentration is 0.0500 m, and the volume at this point of the titration is 12.00 mils, right? And let's say for the acid, so doesn't matter what the acid is, I'm just going to use HA. Let's say that the molarity is 0.200 m, and the volume is, let's say it is 12 mils, right? Okay, so in this case, like we did before, we need to find a number of moles of the sodium hydroxide, which we did before. I'm not going to go through that step again. I'm just going to give you 6.00 times 10 to the minus 4 moles, right? Now, in the case of the acid, the number of moles would be 12.00 milliliters, convert to liters, 1 liter over 1,000 mils, and then we multiply that by the molarity, which is 0.200 moles over 1 liter. So let's see what that gives. So 12 divided by 1,000 times 0.2. Okay, so when I did this calculation, and again, please correct me if I'm wrong, all right? But This is what I got. 2.400 times 10 to the minus, no, hold on. How many sig figs? That should be 3 sig figs. So let me correct this here. So this is going to be 2.40 times 10 to the minus 3 moles, right? Okay, so again, set up our ice table where the reaction is NaOH plus HA to give NaA plus H2O, right? So the initial amounts, mole-wise, would be 6.00 times 10 to the minus 4. This is going to be 2.40 times 10 to the minus 3. This is going to be 0. No need to concern ourselves with the water. The change here, okay, so obviously the limiting reactant in this case is going to be the sodium hydroxide. So therefore the change here is going to be minus 6.00 times 10 to the minus 4. Here you're going to minus 6.00 times 10 to the minus 4. Here you're going to have plus 6.00 times 10 to the minus 4. And then the change, not change. The end of the reaction here, you're going to have 0 here. Here, you're going to have 2.40 times 10 to the minus 3 minus 6 times 10 to the minus 4. So I got here 1.8 times 10 to the minus 3, right? And here you're going to have 6.00 times 10 to the minus 4. All right, so you notice now that this here and this here are not the same, right? So therefore, when you calculate the concentration of HA and the concentration of the A minus, those will not be the same because the volume is going to be the same for both of them, which is the sum of these two, right? The total volume is going to be equal to 24.00 mils. So what we have to do now is calculate the concentrations of HA and A minus separately, right? So let me do that down here. The concentration of HA will be equal to the moles, which is 1.8 times 10 to the minus 3 moles, divided by the volume, which is 24.00 mils. And then we have to convert to liters, so 1 liter over 1,000 mils, right? Let's see what that gives. That gives 1.8 times 10 to the minus 3. Oops. 1.8 times 10 to the minus 3 divided by 24 divided by 1,000. Okay, so for this part, I got rounded off to 2 sig figs. I got 7.5 times 10 to the minus 2m. And then we do a similar calculation for A minus, which would be 6.00 times 10 to the minus 4 moles, divided by the volume, which is the same volume as before, 24.00 milliliters, which again you have to convert to liters, 1 liter over 1,000 mils. And when I did that, let me see here, 6 times 10 to the minus 4 divided by 24 times, 6 times 10 to the minus 4 divided by 24 divided by 1,000. And when oh no, that can't be right. Let me try this again. 6 times 10 to the minus 4 divided by 24. Okay, so what I got here is 2.5 times 10 to the minus 2m, all right? So let me erase up top here. Okay, so because it's a combination, again, of a weak acid and the conjugate base of that acid, then we can find the pH using this equation. pH is equal to pKa plus log of the concentration of A minus the log, divided by the concentration of HA. And then all we do now is put the numbers in. Now, the Ka, what's the Ka for benzoic acid? Okay, so the Ka is 6.28 times 10 to the minus 5 So this will be minus log of that number, 6.28 times 10 to the minus 5. And then we're going to add to that log of A minus, which is 2.5 times 10 to the minus 2 M divided by HA concentration, which is 2.5, I'm sorry, 7.5 times 10 to the minus 2 M. And that's it. So all we have to do now is put the numbers in our calculator. I'm going to work out this part first. So that will be 2.5 times 10 to the minus 2 divided by 7.5 times 10 to the minus 2. And then I find the log of that. And according to my calculation, that would be equal to minus 0.4, is two sig figs, so you need two decimal places, 0.48, right? And then for the other part now, that would be 6.28 times 10 to the minus 5 log, but you have a plus sign here, so that gives you 4.202, right? So now we're going to do 4.202 minus 0.48. And according to my calculation, this works out to be equal to 3.72 as your final answer. And that's how you do that. All right? So you'll notice the difference between this one and the A part of number 3 is that the concentrations of the weak acid and the weak base, the conjugate base, are not the same, right? So therefore, you have to make sure you do that calculation first to find out if they're the same and put the appropriate values into here and here, along with the minus log of Ka. And when you do the number crunching, you end up with your final answer. All right?
Why do we
Oh.
have the negative log for the Ka? Is that just a relationship between
Yeah, that's the
Ka
definition.
and
The definition of pKa, let me show you. pKa is equal to minus log of Ka. And pKb, while I'm at it, is minus log of Kb. pH is minus log of the concentration of H plus. pOH is minus log of the concentration of OH minus. So basically, P means minus log. You see what I'm saying?
Yes.
Yeah, so that's basically what that is about. Okay, any other questions?
Do you think we could go over question 7? I had a question about that one.
Which assignment?
Same one. Assignment
Okay.
number 5.
Okay, question 7. Question 7. Oh, the one that says solubility product constants are usually specified at 25 degrees?
Yes, that one.
Okay, yeah, so basically, the question is asking, how does the Ksp value for a compound depend on the temperature, right? For most ionic compounds, when you increase the temperature, the solubility increases, right? And therefore, if the solubility increases, the solubility product will increase, the Ksp value would increase. And that's basically it, right? If you think of, for example, silver chloride, right? Add it to water, this is a solid, you add it to water, equilibrium will be established, Ag plus aqueous would be one of the products, and the other product would be the chloride ion, right? So basically, that's what happens, let's say at room temperature. And then if you increase the temperature, what will happen is that more of the solid will dissolve to form the ions, right? Now, Ksp would be equal to the concentration of Ag plus times the concentration of Cl minus, right? So, minus. So, if you were to increase the temperature of, this system here, then basically the concentrations of these two would increase, which means that Ksp will increase. So, concentration of Ag plus increases, concentration of Cl minus increases with increasing temperature, which means that Ksp will also increase, right? And that's pretty much it.
So does things like endo and exothermic come into play here when
Well,
the
actually,
temperature increases?
okay, sorry about that. Lost connection for some reason. Can you hear me?
Yes.
Okay, good. Okay, I forgot. What was the question somebody was asking?
I was asking if endo or exothermic will come into effect
Oh,
here if
yes,
the
right.
temperature's increased.
Yeah, good question. So basically, when it comes to this is a kind of rule of thumb when it comes to predicting um whether or not a reaction is endothermic or exothermic. Usually, in the vast majority of cases, if you start off with one reactant and end up with more than one product, then that's an endothermic reaction, right? And that is definitely true when it comes to the example I gave before. See if I can bring it up. I think I lost it. Um, okay, let me see if I can. Okay, right. So going back to this example right here. Right. So basically, in this case, you're starting off with one reactant and you're going to end up with more than one product, right? So usually when you have that situation, that would be an endothermic process, and Le Chatelier's principle would apply. So what that means basically is that if this is endothermic, then delta H would be on this side, which means that when you increase the temperature, you're increasing this, the equilibrium shift to the right to reduce the temperature, and therefore the concentrations of silver and chloride ions would increase, and therefore the Ksp value would increase. And that's it. So yes, endothermic or exothermic would come into play. And when it comes to the dissociation of ionic compounds, um, you'd expect that it would be an endothermic process. All right.
Thank you,
Any other?
Professor.
I'm sorry?
I was just saying thank you.
Oh, yeah, no problem. Any other questions? Any other questions?
Professor,
Yes, sir.
I had a question about assignment 7.
Assignment 7. Okay, hold on 1 minute. Oh, well, that won't be on the test, but I mean, if you want me to
No, it
talk.
is due today. I had like a question
Oh,
about.
okay. Let me see if I can find it. Assignment 7. Let's see. Do I have it here? Hold on. Okay, assignment 7. What question in particular?
So question 1 on part H, like the really last part of question 1.
Oh,
I
okay.
don't know if it's
Hold on. Let me scroll down. Let me scroll down and find it. Okay, H.
so like the rest of the questions they say if it's like in a basic or an acidic solution, but this one doesn't say so.
Oh, right. You can leave it in acidic. That's
Okay.
fine. Yeah.
All right. Thank you.
All right. Any other questions? Any other questions?
I have a question about assignment 7 as well.
Okay.
It was for like the add-on assignment that we did.
Oh, you mean the addendum?
Yes.
Okay, let me see if I can bring that up here. Hold on. Let me see. Oh, shoot. Looks like all right, hold on 1 minute. Let me I thought I had it here. Hold on 1 minute. Let me go to assignment 7. Okay, found it. Okay, which question in particular?
So number 9, like
Okay,
when
hold
we're
on, number
doing it
9.
in
Number 9, number 9, number 9, number 9, number 9. Okay, number 9. Yes, ma'am.
so when we were doing it in class, like you erased what we had for the cathode, anode, and the overall, and you like continued with the other problem. I don't know if you meant to go back to it, but I was just wondering what we're supposed to put for number.
Oh, I think if I remember correctly, I think the error I made was that the uh hold on. What was the issue there? Let me see here.
I think you said like you forgot about the iodine.
Right. Okay, right. Okay, so basically you see where it says number 9, right? The reactions at each electrode. Um, and then it gives you cathode, anode, and overall. Just eliminate all that because basically um number 10 is asking for the same thing. So yeah, just ignore number 9, basically. That's what it comes down to.
Thank you.
I need to remember that too when I'm grading. Okay, any other questions? Let me just say that I'm willing to make myself available tomorrow. Hold on, let me check and make sure. Yeah, I think I'll be able to make myself available tomorrow in the evenings. It would have to be after 2 o'clock. So maybe something like 2 to 6 or something like that. If you have any questions, and if you want to talk to me tomorrow, but let me know. You can probably send me an email and let me know if you need me to come or need me to not come, but to create a Zoom link for that purpose, right? So let me know if you need me to discuss any more problems with you tomorrow, but it would have to be after 2, not in the morning.
Professor,
Yes, sir.
do you think we could also go over number 8B on assignment 5?
Okay, so assignment 5 and 8B. Okay, so 8B is to calculate the molar solubility of lead 2 chromate in the presence of 0.020 m sodium chromate. All right, so this is another example of what we call the common ion effect. Okay, so basically you have two things going on here, right? You have the sodium chromate. Oh, this, I don't like this. Okay, so you have the sodium chromate, which is undergoing complete dissociation to form 2 Na plus chromate ions. And then you have the lead 2 chromate undergoing dissociation, but this one will not be a complete dissociation. So you're going to end up in this case with Pb2 plus CrO4 2 minus. All right. Now, basically what's going to happen is that because of the presence of the chromate from the sodium chromate already in the solution, that will reduce the molarity or the solubility of the lead chromate, because according to Le Chatellier's principle, when this is increased, the equilibrium will be pushed to the left and therefore reducing the solubility of the lead 2 chromate. So what we have to do is set up an ice table. So let me erase this here. So the ice table will involve initially no lead 2 plus, but initially the concentration of the chromate will be the same as the molarity of the sodium chromate, which was 0.020 m, right? Because it completely dissociates, the concentration of this will also be 0.020 m. So the initial concentration of the chromate ion in this case is going to be 0.020, and therefore the change, we're going to say that is plus S and plus S here, because it's a 1-to-1 where S is equal to the solubility. So therefore, at the end of the reaction, or at equilibrium, I should say, you're going to have S and S here. The KSP for this, I'm sorry, S plus 0.020 here. Sorry. You're adding this to this, and that gives you that, right? So the KSP in this case is going to be S. Well, let me just write down the general equation. Concentration of lead 2 plus times the concentration of CrO4 2 minus, right? And then we're going to put these terms into this equation where you're going to end up with S here and S plus 0.020 here. And then we're going to make an assumption. We're going to assume that S is much less than 0.020. So therefore, S plus 0.020 is approximately equal to S. I'm sorry, 0.020, right? So KSP will now be equal to S times 0.020, which means that S will be equal to the KSP divided by 0.020. And the Ksp in this case for this reaction is, what is it? It's 1.8 times 10 to the minus 14. 1.8 times 10 to the minus 14 divided by 0.020. And then when we work that out, 1.8 times 10 to the minus 14 divided by 0.02. According to my calculation, this works out to be equal to 9.0 times 10 to the minus 13. M. And that's it. All right? Any
So,
questions about? Oh, I'm sorry. Yes, sir.
just to make sure I have this correct, the sodium chromate is the first disassociation because we're
Mhm.
given the molarity in the question.
Right, exactly. So it will, yeah,
Okay.
and the important thing you need to recognize is that that dissociation will be complete, right? Pretty much any sodium salt or any potassium salt or any lithium salt will undergo complete dissociation, right? So sodium chromate will undergo complete dissociation. So as a result of that, whatever the molarity of the sodium chromate is, the molarity of the chromate ion is going to be the same.
So you said if it's sodium,
Sodium, potassium, or lithium, pretty much
Okay.
all group 1A metal ion salts will undergo complete dissociation.
Okay.
Mhm. Okay, any other questions about this or any other questions, period? So no other questions?
Professor,
Mhm.
could we go over the final question, question 3 of the practice final for tester?
Okay, so you're talking about let me see here. You said the final, oh, test 3 practice. Okay. So if I remember correctly, I stored that in the past test key folder. Let me see here. So you're talking about tests. Okay. I think I know what you're talking about. Okay, so test number, oh, wait a minute. Test number 1, 2. Okay, so which question in test number 3 are you talking about?
The last one, the
The
final.
last one. Okay, hold
Yep.
on. Hold on. Last one. Okay, hold on. No, that's not the last one. Oh, yes, that is the last one. Okay, so just to be sure, you're talking about the question which starts off by saying the equilibrium constant K for the reaction, PCl5 to PCl3 plus Cl2 is 8.96 times 10 to the minus 2.
Yeah, that one.
Okay, all right. So let me clear this. Okay, so they gave you the equation, they gave you the K for the reaction, and it's asking for a couple of things. The first of which is delta G. Well, again, as we said before, delta G is equal to minus RT ln K. All right? So all we have to do is put the numbers in, R is 8.31 joules per mole Kelvin times T, which is 298 Kelvin, times ln K, and K is 8.96 times 10 to the minus 2. So let's see what that gives. 8.31 times 298 times 8.96 natural log equals, okay, and then I have to round this off to 3 sig figs. So according to my calculations, this works out to be equal to 5.97 times 10 to the 3. And in terms of units, oh, by the way, this should be moles Kelvin here. So the units here would be joules per mole. All right. So this is the first part. The second part is, hold on. Okay. It says use the thermodynamic data in the tables provided to determine delta H for this reaction. So in this case, you have to consult the tables. And the equation is PCl5 to form PCl3 plus Cl2, right? So what you have to do is go to the tables and look up the delta, what is it? Delta H? The delta H values. Now, here's the thing. Chlorine is going to be 0. We know that already. And if you look up the PCl3 value in the tables, you're going to see that this is minus 287.0 kilojoules per mole. And the value for PCl5 would be minus 374.9 kilojoules per mole. So delta H standard would be equal to minus 287.0 kilojoules per mole minus 374.9 kilojoules per mole. And when you do that calculation, 287.0 374.9. So the answer I got is 87.9 kilojoules per mole. And that's it. All right. Oh, is there more to it? Let me scroll down some more to see. Oh, okay. So now that we have delta H, I thought that we had, stopped or reached the end of the question, but there's a third part. The third part says, using the answers derived from 1 and 2 above, calculate delta S. Now, remember, the relationship between delta G, delta H, and delta S is delta G standard is equal to delta H standard minus T delta S standard, right? What the question is asking for is this right here, delta S standard. So delta S standard is equal to delta H standard minus delta G standard over T, right? So if we were to do that calculation, delta S standard, we're going to plug the numbers in, is equal to delta H standard. What's delta H standard? 87.9 kilojoules per mole, right? Minus delta G standard, which is what we have here, which would be 5.97 times 10 to the 3 joules per mole. But because we have kilojoules here per mole, we have to convert that to kilojoules here. So we're going to multiply by 1 kilojoule above and 1,000 joules below. And then we're going to divide all of that by the temperature, which is 298 Kelvin. And let's see what that gives. So I'm going to work out this part first. In fact, I can just see that this would be equal to 5.97 because this 1,000 will cancel out this 1,000 here. So let me do the rest. 87.9 minus 55.97. And then after that, I'm going to divide by 298. And according to my calculation, this works out to be equal to 0. How many sig figs? 3 sig figs. So 0.275. And the units here would be kilojoules per mole Kelvin. And usually this is expressed in joules per mole Kelvin. So therefore, if you multiply this by 1,000, this becomes 275 joules per mole Kelvin. All right. So that's basically how that is done. Okay. Any other questions in the remaining 14 minutes? No more questions? Well, does that mean you're all set?
Yes, we're good. Thank you for your help.
Okay. All right. Well, if that's it for today, that's it. Like I said, I can make myself available tomorrow after 2. So if you're interested, just shoot me an email. I'll be checking my email between now and tomorrow morning. And just let me know if that's okay by you guys so I can make arrangements for that to happen. All right. So with that said, I bid you all farewell and enjoy the rest of your weekend.
Yes, you too.
Mhm.